Okay, recording started. Let's share the screen, then we can start. Good afternoon, everybody. Today's lecture, we will start our new section or new topic, which is related to the substations. So basically, we will talk a little bit an overview in designing sub-transmission lines and distribution substations. So the overall, as we know, the power system consists of, or electrical power system consists of generation, transmission, and distribution. So let's assume that we need to supply the power, for example, to our campus, to German Jordan University. So assume we have the university substation here, then we need to supply power to it. So the substation, we used to donate it by a bus bar. So let's assume this bus bar for GJU, for the university symbol. Then we will donate the load by this arrow. So this is the load for the university. Then the university substation is called GJU. Then how the things goes, or how the power goes, the overall, we have a generator. So the generator power generation used to be as, or can be donated by a voltage source. So here is the generation donated by a voltage source. So I assume that you already aware of the single line diagram. So the generation can be donated by this source. Then from the generation, basically, we need to transmit the power. So the power or the voltages at the generator most likely will be within around 15 kilovolts. The 15 kilovolts is not sufficient to supply power for very long distance. So for instance, if you need to supply the power for a destination around like 200 kilometers or 300 kilometers, 15 kilovolt will not be sufficient. Why? What's the point of making this insufficient? Which is basically, assume this is a generator and we need to transmit the power, for example, for very long distance, like 400 kilometers. Then here is the load. Then we can say, when you look at the load and the generation, look at the transmission line. So here, these wires or the transmission line has its own impedance, which is impedance of transmission line. How can we calculate the impedance of the transmission line? This is in a separated course, which is in power system course. But I would say, like, let's assume a short transmission line. Then in short transmission line, basically we can say the Z of the transmission line is R plus JXL. Then look at the resistance, for example. The resistance, as we know from physics, which is rho times L over A. Rho is related to the material, A is related to the cross-section area, then the remaining, which is the length. This is the remaining. So we can say the resistance depending on the length. Once, when you increase the length, the resistance will increase. Okay, so what's the point of that? Look at the losses here. There will be some losses. So we can donate the system by a voltage source, resistor of the transmission line. For example, assume the reactance is neglected, or you can include it, whatever it is. Then after that, we have a load. Then the losses in the transmission line, which is basically P loss. The loss is I square times R. So we can notice that the losses in the transmission line, I square times R, you can see it's depending on I, depending on R. R, which is depending on the length, as I said here. Since it's depending on the length, once you increase the length, the resistance will be increased, which make the losses increased. So if you increasing the distance, if you transmit the power for 300 kilometers, it will be very long. I mean, a lot of there will be a lot of losses. If you transmit the power 500 kilometers, then it will be more losses and more. If you increase the distance, will be more losses. Then if you keep the voltage as 15 kilovolts, it will not be sufficient to transmit the power to reach the load, because most likely the generator will supply the losses, or the losses will be more than the load, which is something that not desired or something undesired. How can we overcome this? By using the transformer. So the transformer principle, which is basically step up the voltage. As we know, the power equals V times I, conjugates. So let's assume the power is constant. Once you increase the voltage, what will happen to the currents? Which is basically, it will be decreased. Since the current decreased, what's happening to the losses? The losses I squared times R, then the losses will be decreased as well. As a result, losses will be decreased, then the losses decreased, then the overall the losses will be decreased, which make the system more increase efficiency, reduce the losses. Therefore, in order to transmit the power for long distances, we need to add a step-up transformer. So we will add a transformer here. That transformer, a step-up transformer, can convert the voltage, for example, from 15 kilovolts to be 132 kilovolts. This is a step-up transformer. Then, after that, we need to transmit the power to, for example, to the campus, to German University, Jordanian University, whatever it is. So we need to transmit the power. That's the thing. Then it goes toward a substation, the closest substation. Then here we are transmitting the power, for example, let's assume 100 kilometers, and it is in 132 kilovolt, which is basically high voltage level. High voltage. Then once we reach close to the campus, so I would say, for example, the closest substation, electrical substation, the closest one to the campus, which is basically Madaba substation. So here, for example, Madaba substation. So Madaba substation, basically there will be a transformer inside that substation that's converting 132 kilovolts to be 33 kilovolts, which is basically step down. Keep in mind, when we did the step up 15 kilovolts to 132 kilovolts, we did it instantaneous at once, in one time, in a single shot. However, when we are doing step down, we won't do it, I would say, like in one step. We will do it in several steps. So we'll do it small step by small by small. Then we transmit the power 132 kilovolts to 33 kilovolts. This is once we reach this 33 kilovolts, it will go toward GJU, which is our campus. It will go toward that. Then after the 33 kilovolt, or after Madaba substation, it will be in medium voltage, because 33 kilovolt is based on medium voltage. So we can say here medium voltage. Okay. Then it will go to the university here, to Jordan University. Then the thing here, there is a substation very close or inside the campus that's converting 33 kilovolts to 0.4 kilovolts. Then it goes toward the load, which is to the buildings, like C building, A building, whatever the buildings that we have. It will go to the several buildings, then goes to the load. So we have a small substation inside the university that's making the transmission, we call it, making the step down transformer from 33 kilovolts to 0.4 kilovolts. Okay, so again, we have 33 kilovolts to 0.4 kilovolts. So what's 0.4 kilovolts? Remember, we are talking about three-phase. So V line to line equals 0.4 kilovolt, or in other words, it is 400 volts. However, if we are connecting the power for a single phase, then we can say V line to neutral equals V line to line divided by root of 3, which is 400 divided by root of 3, then it will be 230 volts. This is the home voltage, or the voltage at the wall outlets and the voltage at like inside the buildings. That's where 230 volts or 400 volts comes from. Again, 400 volts associated with line to line, while 230, that the voltage that we know, which is associated with line to neutral. Okay? Then we can say, look at the first part. This is associated with the generation substation. Then the next one associated with the transmission. Then after that, during the medium voltage level, it will be associated with something we call it sub-transmission. Then the last one, we are going to close to the university or to the campus. This is we call it distribution. So as a result, we have four things: generation, transmission, sub-transmission, and distribution. I would say in Jordan, we used to mix between between distribution and sub-transmission. So we have generation with, like for example, a Samra generation, or for example, rehab generation units, IPP3, IPP4 generations. Then we have transmission. In Jordan, there is only one company associated with the transmission, which is called NIPCO, National Electric Power Company. Then we have sub-transmission and distribution. Usually, sub-transmission and distribution, they will be with one company, which is, we call it the distribution company. Or, for example, in the middle section in Jordan, we have, which is called JIPCO, which is Jordanian Electrical Power Company, شركة توزيع الكهرباء الأردنية. So the thing here associated with the sub-transmission, when you go to this company, you will see there are two parts. The first part associated with the medium voltage or associated with the sub-transmission, then the second part associated with the low voltage, which is the distribution. So I would say in generation, it is based on medium voltage, then we are stepping this up to be high voltage. The transmission is associated with high voltage, sub-transmission associated with the medium voltage, distribution associated with the low voltage. But again, usually in Jordan, when we talk about the distribution company, we mean sub-transmission and distribution. However, in the electrical engineering perspectives, sub-transmission is separated than from the distribution. So distribution associated with the low voltage, while sub-transmission associated with the medium voltage. The other thing, like how that looks like, the transmission line looks like. In high voltage, the transmission looks like as towers. High voltage as towers, big towers, like very big towers like this shape. However, this is in high voltage and extra high voltage. High voltage, what I mean by high voltage, 132 kilovolts. Extra high voltage, I mean this, which is 400 kilovolts. While this is high voltage. In sub-transmission, this is what there was in transmission. However, in sub-transmission, it comes as a utility pole. Sub-transmissions as a utility pole. Here's a pole. Then basically it can be, let me draw it in the right way. So like this across arms. Then we have a wire goes here, wire goes here, wire goes here. We will talk about it in deep details. This is just an overview. So like a pole, it comes as a pole, not as a tower. Then basically sub-transmission associated with 33 kilovolts, 11 kilovolts, and we have some cases 66 kilovolts. This is very rare, so almost none. Then the last thing is the distribution. The distribution, which is the normal distribution pole that we know, which is consists of several three phases and a neutral, street lighting, and ground. That's the utility pole, the normal utility pole that we have. This is in distribution. So distribution voltage, again, less than 1 kilovolts. So we can say like this is low voltage when we talk about the distribution, and it is zero point 0.4 kilovolts. While subtransmission, as I said, 33 kilovolts or 11 kilovolts, which is based on medium voltage. And again, there's very few cases, 66 kilovolts. So then again, now the thing that I need you to know, which is the transmission voltages are associated with high voltage and extra high voltage. Sub-transmission associated with the medium voltage, distribution associated with the low voltage. This is a very important thing. And the other thing, which is the voltage associated with extra high voltage, 400 kilovolts, high voltage 132 kilovolts, medium voltage 33 or 11 kilovolts, distribution which is zero point 0.4 kilovolts. Those are very important information. All right. Now, distribution system is the part of the electrical utility between the bulk power sources and the customer. What do I mean by bulk power source? Which is basically the grid, the utility grid, the thing that comes, for example, all of this, I can call it bulk power source, like the thing that I did it in purple. This is a bulk power source. So we can donate this by a voltage source as a shortcut with 132 kilovolt or whatever you want to call it, depending on the voltage level. Okay, then basically we would like to supply the power from the source to the customer. So we need to make sure we have a sub-transmission system. Again, those are utility poles. Again, we will talk about this in deep details later. And we have distribution substation, distribution primary feeders, and transformer, secondary circuits, service drops for meters and for protection as well. Here is how the power system overview. This is an example of a single line diagram. This is called single line diagram. Why it's called single? Because it's based on a single phase model. We are assuming the system, three-phase system is balanced, then we don't need to draw three phase on each line. Then basically we can donate it by a single phase or single line diagram or single phase diagram. So assuming approximated it as a single phase, then draw it as a single phase. But keep in mind, all of them are based on three phase. So this is the single line diagram of a substation that's outside of Jordan, actually, but you can apply the same thing in Jordan. So you can say, for example, this is Al-Sbehi substation, this is Madaba substation, this is Salt substation, Sweme, this is the Shamal Amman, South Amman, East Amman, etc. Irbid, Shtefena, um, and so on. So in Jordan, when you go to the control room basically whereas they are controlling and monitoring the electricity of Jordan, for the whole country. Then you will see a screen, a very big screen like this. In this very big screen, you will see all of the electrical substations in Jordan. You will see, again, as I said, like Aqaba, Suwayme, North Amman, Qatrane, Attarat, etc. Whenever Ma'an, Irbid, and the new Jarash substation. So you'll see all of them here, and you will see all of them are in green. And green means there is some energy. Whenever you see something in red, red means it's out of service or power is off. So that's what you will see in the control room, something very similar, but here it's not colored. But I would say like in control room, you will see it colored. And when you look at it, you will see the bus bars. The bus bar associated with the substation, as I said. Like, for example, this association with Bartlett, this is with Meadows, Fairview, Lambert, etc. Lambert, Sierra, Bakers, Springfield, Montgomery, Eco, and so on. This is the bus bar. The other thing, the squares are associated with the circuit breaker. All of any square is based on associated circuit breaker. Whenever you see red and with X means it's out of service. Whenever it is just like square and the green means it's on service. So the circuit breaker is off, or when there is X means open, here means closed. Okay. The other thing, the transformer, this is the transformer, basically. The transformer, we know the transformer simple. And this arrow here associated with the load. Then the generator associated with this is a generator with a circle. Then basically, again, the control room, they have the capability of monitoring the voltage, monitoring the power flow from line to line, from which line, from the substation, this substation, from this line, the other line. They have the capability of controlling the circuit breakers and controlling the other part of equipments. Okay, this is how the circuit breaker single line diagram looks like. Again, this is in the control room. And in Jordan, we have the control room. This is owned by NIPCO, National Electric Power Company, and it is in South Amman, in Al-Mqabaliin, the control room. They are controlling the electricity in all of Jordan, especially high voltage and extra high voltage. However, if we are talking about medium voltage and low voltage, I would say, let me say about medium voltage, there is another control room that owned by JIPCO, Jordanian Electrical Power Company. I think it's in Mecca Street. So this is another control room. Control room. But which one is governing the or controlling the electrical system of Jordan? The one by NIPCO. This is the most important thing. However, the control room by JIPCO, توزيع الكهرباء الأردنية, this is still very important, but it is not controlling the whole of electricity of Jordan. NIPCO is controlling everything, which is the system operator. We will talk more in deep details about the electric system in Jordan later, maybe on the next chapter, maybe next week. I'm not sure, maybe next week or the week after next week, but it will be in the next chapter. Okay, so again, this is the bulk power system. We have the sub-transmission. Again, the sub-transmission, it is here 33 kilovolts. Then from the sub-transmission, it depends on the type of the system. So sometimes some type of the systems, it goes directly from 33 kilovolts to a distribution transformer that's converting 33 kilovolts to 0.4 kilovolts. This is very common in rural areas. However, inside the cities, inside the downtown areas, we doing it in different steps. So this is 33 kilovolts. We have the distribution substation that converting 33 to 11 kilovolts. Then here is 11 kilovolts. Then from 11 kilovolts, when we are going close to the neighborhood or close to the area, then we will convert 11 kilovolts to be 0.4 kilovolts. So sometimes 33 kilovolts will be converted directly to 400 volts or 0.4 kilovolts, or sometimes it will be converted in steps. The first step, 33 kilovolt to 11, and the second step, 11 to 0.4 kilovolts. So which one is used? Again, this part is used in rural areas, inside towns, very small towns, rural areas, or very small towns. However, this part is used in populated areas, where it's basically in very big towns or in cities, inside cities, and especially in city center, very close to the city center. Then we will have it like in these steps, converting 33 to 11, then from 11 to 0.4 kilovolts inside the cities. Which one is better? Which one is safer? I would say, like, I would recommend converting 33 kilovolt to 11 kilovolt, then from 11 to 0.4. However, again, due to the costs, we don't want to make a very big substation inside the towns, small towns. Then we can say it's cheaper to convert 33 kilovolt to 0.4 kilovolts. But what's recommended, of course, the one that I recommend is 33 to 11, from 11 to 0.4, which is very safer. Then from 0.4 kilovolt, it will go to the customer. It will go to your home based on 0.4 kilovolt, or again, this is the same thing as 0.4 divided by root of 3, which is 230 volts as line to neutral. Okay, any question? Please, if you have any question, please, you're free to ask. Okay, so I'm assuming everything clear. The other thing now, we will talk about something we call it radial transmission and loop. So what's the difference between radial and loop? Look at this radial. Here is a substation here, and there's a substation here, substation here, substation here. So you can notice that this is based on radial. Radial, the power goes here, goes here. If, let's assume there is something wrong. For example, this line was out of service due to faults. If this line was out of service, this area will be out of power. Is there any backup power to supply? No, it is out of power. So if there is something wrong in the medium voltage lines or in the sub-transmission voltage lines, this will make the power disconnected from the rest of the customer or from the customers of this area. This will make a big problem. So there will be no backup power. Then they will be disconnected. This is the radial, and this is the drawback of the radial system. How about, can we improve it? The answer, yes, we did some improvements, improvement of radial subsystem. So by adding selector here, a switch. So if, for example, the power was out of service in this line, then the selector will switch, will move from here to here, then it will take the power from this line. So the power will keep flowing from this line. Then we have a backup plan by converting the switch selector from this part to this part, from this part to this part. This can be good, it's improved, but having a selector switch might not be a good idea. But we can have it. I mean, it can help sometimes, somehow, but sometimes, again, the selector might not be a good idea, especially when it is energized, when this one is energized. When the selector moves from here to here, it will cause a big spark, which is something sometimes inconvenient. Therefore, it is a good, better than the previous one, but it's not still not the perfect option. How about this one? The loop type. Okay, the loop type like this one. Loop type, assume the power is out from this part. So there is no power from here. How can the power supply this unit or this unit? It will go from the other source. From this source, from this source. So we still have power, even though there is a line outage here, we still have the power from the other lines. That's a good idea. How about the rest? Let's assume the opposite, or the other line. I mean, assume this line was out of service. How can we supply the power? We still be able to supply the power from this line, and we have the power from this line. Then there is no problem. We still have a source to supply the power from the other direction. So this is loop, and that loop, which of course is the best option. Okay, since it's the best option, why the existing power, why in the existing power system, for example, in Jordan, we have both? Why we have loop and radial? Why don't we have just loop, since the loop is the best? The answer is depending on the costs. Because loop sub-transmission, very costly, will cost a lot of money in doing that. And basically, I would say loop sub-transmission, basically based on 11 kilovolts, the vast majority of the loop sub-transmission based on 11 kilovolts. So we have sub-transmission converting 33 to 11, then the 11 kilovolts will be done as a loop. And many loops comes as underground cables as well. So it is very costly to have a loop. Therefore, in rural areas or in areas like in towns, small towns, we don't like to spend too much money for a light load. Then basically, we will do like a radial. That's the first thing, because the very light customer. The other thing, in rural areas, the accidents are very small. The chance of getting accidents are very small. And the other thing, if the power was disconnected from that rural areas, it is not a very important load. It's not as much as inside the cities. Therefore, inside the cities, we put loop types. So loop types, of course, it's inside the cities. So if there is one line out of service, the rest of the system can still supply the power for the system without any interruption, to avoid any power interruption from the customers. That's, I mean, the advantage of the loop. And of course, it's inside the city, so you can find it, for example, like in the downtown, Amman downtown area, in Abdun area, in, for example, like Irbid downtown, etc. So you can see it's based on loops. However, when you are going outside of these, like go to the close to the towns, small towns like Qura, then it will be basically based on radial. That's what we will see. Again, because the cost. Radial is cheaper than the loop, while the, like here, like radial, which is cheaper, and it is used in, which is, I would say like outside, out of town, or I would say like in towns, not inside the cities. Then the other thing, um, it has the ability to reduce the power. It's, I mean, while when we talk about the loop, which is more expensive inside the cities, but it's more reliable. More reliable. Okay, so that's the advantages of the loops over than the radial. But I would say, I mean, many systems in Jordan are based on radial. Many systems. While loops, again, you will find them in inside the cities or like close to the city centers, and downtown areas. Downtown areas. Okay. The other thing now, I mean, a lot. I would say like in loops, the vast majority of the loops are underground cables. Underground cables, while the radial overhead. I mean, it's not a must, but I would say many overhead transmission line, many loops are based on the down, I would say like underground cables. So here is again, this is underground. So the loops again, underground cables. That's why when you go to Amman downtown, you will see a substation called the Abdali substation. But in that substation, you will not see any high voltage pole or high voltage tower or any medium voltage pole. You cannot see them because all of them are underground cables. The thing, if you are making an overhead, which means you need to pay a lot of money on lands, purchasing the land, because you need to give money for the landowners because you are using their lands to put the power lines. The other thing, when you go to the industrial areas, I mean, when there's a lot of pollution, it will be impacted because of this. The other thing, also, when you go to the Abdun substation, all of the power lines inside it are based on underground cables. That's why we have this in the Abdul substation, it's underground. Why? I mean, which one is better, underground or overhead? I mean, we will talk about this, of course, later, but I would say underground is better because it is, I mean, when you put it underground, you will not, I mean, the people will not be impacted by that, by those lines. That's the first thing. The other thing, you don't need to purchase a land or piece of land or pay money for the landowners to put the transmission lines. Then, I mean, if there is some car accident or something like that, they will not hit the utility pole or they will not hit the tower, then they will not make damages. Then it will be more reliable. But the problem is the cost. The cost of underground cables is too much. I mean, it's very, very expensive to install an underground cables. So the way cheaper is to make overhead transmission line, and way cheaper is to make it radial. However, if you're making it, I mean, loop or making it underground, it will be more expensive, way expensive. Here is, I mean, like system grid or network type systems, then we can see, as we can say here, it is based on a radial. This one, I mean, obviously like based on a loop, not a radial, sorry. Okay, now here is how the substations looks like. This is a substation converting high voltage to medium voltage. You can look at the tower. This is a tower associated with the high voltage. Then you can look at the system here. We have three things. I mean, from each line, there is a three things. And there is a three devices. What's the point of three devices? Because three phase. So it's based on a three-phase system, three phase. Therefore, this is phase A, this is phase B, this is phase C. This is phase A, B, C. A, B, C. And the same thing for the rest of equipments, which is A, B, C. Then the other thing, when you look at this image, you will look at these bars. So what's these bars? This is actually bus bar. This is the bus bar that we were talking about. Do you remember the bus bar here in this single line diagram? We said this is a bus bar, this is a bus bar. How they looks like in real life? Here they are. This is a bus bar. This is the bus bar that we donated by this symbol. And this is the transformer. This is the transformer. So we donated the transformer by this symbol. Okay? We will talk in deep details about what each symbol means, but here, just like for your information, this is based on a three-phase transformer, ABC, and basically this transformer is converting 100, based on my experience, converting 132 kilovolts to 33 kilovolts. This is in Jordan. This is an electrical system in Jordan. How the transformer looks like, what's inside the transformer, how about the other or the rest of equipments, we will talk about it later in deep details. But I would say, again, this is based on a three-phase system. Now, there is something in mind. As we know, in the three-phase system, it does include phase A, phase B, phase C, and neutral. Okay, so where is the neutral here? In this graph, we see only A, B, C. There is no neutral. Okay, so where's neutral? The thing about it, when we are doing transmission and sub-transmission, we are assuming the load is balanced. What do I mean by a balanced three-phase? I would say like balanced three-phase. Balanced three-phase, which is basically, here is, for example, VAN, here is VBN, here is VCN, which is 120 degrees phase apart. So as a result, if the system is balanced, we can say VA, or also let me talk about the currents. IA plus IB plus IC equals 0. And this is the same as I neutral. So as a result, the neutral current is 0. Since the neutral current is 0, there is no need to install a fourth wire. It is already 0. The neutral current is 0. And the other thing, in the transmission and sub-transmission, we used to transmit it by delta. And as we know in delta, there is no neutral. So in transmission, sub-transmission, no neutral. We are transmitting the power only on three wires, A, B, C. However, when we are going to the distribution, there will be a neutral. The neutral is a must. So there must be a neutral. Again, we will talk more about this deep details in the future courses. I'm sorry, in the same course, in the future chapters, I'm sorry. Okay, so again, what we discussed so far to conclude, I think we talked about the generation. So the generation associated with the medium voltage, and there is a transformer, step-up transformer. There is generator, step-up transformer. And we call it denoted by GSUT, generator step-up transformer. Then after that, we have a transmission. The transmission can be high voltage or extra high voltage, which is it can be 132 kilovolts or 400 kilovolts. I'm talking about it in Jordan. However, in different part of the world, we have another voltage level like 230 kilovolts, 115 kilovolts. That's in the United States. We have 500 kilovolts and 400 kilovolts. Those are the voltages in the United States. While in Jordan, we have 132, 400 kilovolts. That's in Jordan. This is associated with high voltage and extra high voltage. Then the next thing, which is subtransmission. And with subtransmission, it is based on medium voltage. Medium voltage can be 33 kilovolts or 11 kilovolts. And we mentioned about the subtransmission can be either radial or loop. That's the subtransmission. Then the last thing, which is the distribution. So the distribution, we have low voltage, which is 0.4 kilovolts. Again, the other thing related to the neutrals, there is no neutral, no neutral. Here in subtransmission, no neutral. Distribution, neutral is a must. Okay, then the neutral must exist. Okay, any question? Okay, I think that's it for today. Before finish the meeting, any question, please? Any question, any comments? All right, now me stop the recording.